Welcome. Today we shall discuss supermassive black holes. Supermassive black holes that reside at the center of radio galaxies that we discussed in the previous lecture. The central engine of quasars in general have luminosities of the order of 10 to the power 46 to 10 to the power 47 ergs per second. Let me remind you that the luminosity of the Sun is a mere 4 times 10 to the power 33 ergs per second. The central engine is generally of radio galaxies is generally a quasar, which is shorthand for quasi-stellar radio source. This is invariably at the center of a giant elliptical galaxy and never a spiral galaxy. A luminosity of 10 to the power 47 per second is more than 10 to the power 10 times the luminosity of even very massive stars. Such a luminosity implies that the mass of the central engine of quasars must be more than 1 billion solar masses, 10 to the power 9 solar mass. And how do we come to this conclusion? Let me now explain. Let's go back to Eddington's luminosity limit, which I have now discussed several times, but let me do this once again because this is an extremely important concept. If you remember, Eddington introduced the notion of radiative equilibrium. In other words, the inward pull of gravity is balanced by the sum of gas pressure plus radiation pressure. As one goes to more and more massive stars, radiation pressure becomes more and more dominant, till finally in very massive stars, the pressure due to gas is almost negligible. Let us consider such a situation. Let us consider a unit volume that I show here inside the star. And let us assume that this unit volume is in radiative equilibrium. In other words, the pressure due to radiation acting on that unit volume is precisely equal to the gravitational force per unit area due to the mass interior to this unit volume. Now, the radiative force on the unit volume is given by this simple expression over there. Now, we discussed this in detail in lecture number 3 on why are the stars as they are, but you've probably forgotten, so let me quickly remind you where this comes from. L is the luminosity generated by the star at the center. Therefore, L divided by 4 pi r squared is the energy crossing a unit area per unit time on the surface of an imaginary sphere whose radius is small r. And that energy flux divided by c will give me a momentum flux. That is the rate of momentum transfer per unit time. Now, pressure, now I have to multiply to calculate the total radiative force on the unit volume. I have to multiply that by the effective area of whatever is in there in the unit volume. Now let us consider, for the sake of simplicity, that unit volume consists of electrons and protons. So the star is essentially hydrogen. Each electron subtends a cross-section which is given by the Thomson scattering cross-section. And there are n electrons per unit volume, and therefore this is the total cross-section of all the electrons in the unit volume. Now you will say, what about the protons in the unit volume? Well, protons, since they are 2000 times heavier than the electron, the radiative force on the proton is less important than the radiative force on the electron. Therefore, I have considered only the electron. So this expression over here is the radiative force acting on the unit volume over there. As I said, the radiation force on the proton will be negligible in comparison. Now, let us recall what is Thomson scattering cross-section. The Thomson scattering cross-section is 8 pi by 3 multiplied by the square of the electron radius. And the electron radius is defined by this relation that the electrostatic energy E squared over Re is equal to the rest mass energy mc squared. And what is the gravitational force acting on that unit volume? That is G mass interior to R multiplied by the mass of the unit volume, which is the number of protons per unit volume multiplied by the mass of the protons. Here I have neglected the electrons. So as far as gravity is concerned, it is the protons that matter. As far as the radiative force is concerned, it is the electrons that matter. Therefore, the gravitational force acting on the unit volume is Gm times nmp divided by r squared. For radiative equilibrium, the gravitational force acting on the unit volume must be precisely equal to the radiative force acting on the unit volume. And that gives us the luminosity, which is known as the Eddington luminosity. Now let's look at this expression carefully. The most remarkable thing about this expression is that apart from fundamental constants, this luminosity, whose significance is that this is the maximum luminosity a star can have, is uniquely determined by the mass of the star. The radius of the star or the temperature of the star does not come into the picture. And that maximum luminosity of a star of mass m is given by this formula that L Eddington is 10 to the power 38 ergs per second, the mass of the object divided by the mass of the sun. I have chosen to write it in units of the mass of the sun. If the luminosity of a star, any body were to exceed this luminosity, this limiting value, then the radiation pressure will overwhelm gravity and the object will be disrupted. Therefore, a luminosity of 10 to the power 47 ergs per second implies that no matter what the mechanism of radiation is, the mass of the emitting body has to be in excess of 10 to the power 9 solar mass. In other words, if I put 10 to the power 9 solar mass there, solar mass gets cancelled. So 10 to the power 38 multiplied by 10 to the power 10 to the power 9 will give me 10 to the power 47 ergs per second. So that's the argument. That is how we deduce that the central engines of quasars must have a mass of at least a billion solar mass in order to radiate 10 to the power 46 or 47 ergs per second. As I said in the previous lecture, a couple of years after radio galaxies were discovered, astronomers were stunned when they found that the radio flux from the quasar varied over a time scale of a year. Now, this was the most unusual thing. One had never encountered variability of this nature. And that's what is shown here, radio variability. You can't read the x-axis over there. It is of the order of a year. Now, this immediately suggests that the central engine must be a supermassive black hole. Why? If an object is variable with a variability timescale delta t, then as I explained in the previous lecture, and even before that when we discussed pulsars, then the radius of the object must be less than c times delta t, where c is the speed of light. Therefore, if you put for delta t 1 year, then you get a maximum size for the emitting body. Now, we have already concluded that body must have a mass in excess of 10 to the power 9 solar mass. Therefore, if you pack 10 to the power 9 solar mass into such a small radius, then it is either a black hole, the gravitational radius being 2 gm by c squared, or will soon, due to some instability or other, become a black hole. Now, a few years later, optical astronomers discovered that quasars were variable even at visible wavelength in the time scale of a few days. So the argument for why the central engine must be a supermassive black hole became even stronger, because delta T now was not 1 year, but just a few days. Then a decade or so later, X-ray astronomers discovered that quasars were variable in X-rays also, but this time the variability was not in a year or a few days, but it was of the order of a few minutes or about an hour or so. Therefore, this variability in the time scale of a few minutes or an hour was the last nail in the coffin, as it were. And that tells us very definitively that the central engines of quasars are either supermassive black holes or will soon become supermassive black holes. Thus emerged the picture that quasars, as well as other types of active galactic nuclei, are powered by supermassive black holes. Now, with the advent of the Chandra X-ray Observatory, it has emerged that all galaxies, including our own Milky Way galaxy, harbor supermassive black holes at their centers. They may not all have a mass of 1 billion solar mass, but they may have a mass of few million solar masses. Now you might ask the question, if there are supermassive black holes at the centers of all galaxies, then why are there no active quasars at the centers of all galaxies, including our own galaxy? And the reason is, although you may have a supermassive black hole at the centers of galaxies, in order for it to function as a quasar, you must supply it with gas so that gravitational potential energy is released. So if a supermassive black hole is starved of matter, then it will be quiet and therefore not function as a quasar. So, to repeat again, unless sufficient matter accretes onto the black hole, there will not be much radiation. The 3 million solar mass black hole at the center of the Milky Way galaxy is an example. As one astronomer said, it is suffering from malnutrition. It isn't being fed enough for it to function as a quasar. Now, stars and gas clouds, which are in close orbit around the central black hole, can be tidally disrupted if they come sufficiently close, and then the gas can fall into the black hole. Similarly, gas clouds, atomic gas clouds, molecular gas clouds, can fall into the black hole. In every case, because the matter, whether it is a star or a cloud, because it's orbiting the central black hole, the infalling matter has to first form an accretion disk because there is a large amount of orbital angular momentum. So the accretion disk is like the ring system of Saturn. Now, due to friction between the orbiting particles of the orbiting gas, the gas spirals in and eventually falls into the black hole. And in that process, gravitational potential energy is released. Gravitational potential energy released in radiation is not a very efficient process in the case of a black hole compared to a neutron star. the efficiency is only of the order of 10%. Most of the mass is just gobbled up by the black hole. The amount of energy actually released in the process of infall is somewhat less than in the case of a neutron star. Now, for a luminous quasar, the black hole has to accrete several solar mass of material every year. Now, that's a lot of mass. So, unless you feed the central black hole with many solar mass worth of gas, it will not function as a bright quasar. So what is shown in this figure is the central black hole, a supermassive black hole in this case, and there is an accretion disk, a thin accretion disk. I've shown the accretion disk as extending only up to there, but that's because if I had extended it further, it would go into this text over there. So the accretion disk is rather large. Detailed studies, calculations have demonstrated that the innermost portion of the accretion disk is puffed up as shown in this figure. It is puffed up because of radiation pressure. Radiation pressure makes the accretion disk swell up, and you have, of course, you have to remember this has to be viewed as a figure of rotation. Therefore, what you have is something like a donut with a hole, a narrow hole in the center. So you have a nice funnel, and this funnel is supposed to help in the formation of jets, which we discussed in the previous lecture, relativistic jets going along the direction perpendicular to the plane defined by the accretion disk, which is usually the equatorial plane, but doesn't have to be the equatorial plane. As for how the jet material is accelerated to relativistic speed, a very clever mechanism was suggested by Blanford and his collaborators many years ago, and it is very similar to the pulsar. If you remember, in the case of the pulsar, there is a magnetic field threading the neutron star, and because of rapid rotation, a very strong electric field is formed outside the star, and the electrostatic force due to this electric field pulls out the charges from the surface of the star, which then slide along the curved field lines like beads on a string, in the process radiating. Now, in the case of a black hole, as we discussed, black hole cannot have a magnetic field, but an accretion disk can have a magnetic field because the accretion disk is composed of ionized matter. So, this mechanism of Blanford and his collaborators uses the magnetic field threading the accretion disk and the consequent strong electric field generated in the disk. So it is very similar to the Goldreich-Julian mechanism that we discussed when we talked about pulsars. Remember, once again, unlike a neutron star, a black hole does not have a magnetic field. Therefore, this problem is more subtle and more difficult than the problem of relativistic wind from a neutron star. The last word on how a relativistic jet is generated and collimated has not been said yet. One still has to collimate the jet and re-accelerate the jet over a distance of 1,000,000 light years before we can explain the radio lobes and the hotspots of radio galaxies. So that problem still remains to some extent, but we shall not digress to discuss that problem. Now, as I said in the previous lecture, there is a zoo of active galactic nuclei, all powered by supermassive black holes. They go under various names and they have various properties. There are Seyfert galaxies, there are BL-like objects, there are quasars, there are QSOs. These are quasi These are radio quiet quasars. These are quasars, point-like objects, but they are bright in the visible X-rays and so on, but they are quiet in radio. Previously, till about 20 or 30 years ago, there were different theories about emission from Seyfert galaxies, BL-lax, quasars, QSOs, and so on. Now, in recent times, a unified picture has emerged, which is shown over there. Right in the center, where I'm pointing, is the supermassive black hole. There is an accretion disk in the equatorial plane. That disk is very thin, but right close to the black hole, that thin accretion disk is puffed up to an enormous size compared to the size of the black hole. It is puffed up because of radiation pressure. Surrounding this accretion disk, there is a torus. This torus consists of dust and molecules, presumably these giant molecular clouds in orbit around the central black hole. This has been deduced from observations. And then there are also various clouds, atomic clouds and molecular clouds. Now, what is irradiating these molecular clouds and these atomic and molecular clouds? It is the X-ray radiation from the accretion disk. The accretion disk is very, very hot, temperature of the order of 10 million degrees. Therefore, it will be radiating in soft X-rays and far ultraviolet. And that radiation interacts with these clouds and molecules and produces various kinds of phenomena. So depending upon how you view this system, whether if you view it, for example, along the equatorial plane, then the astronomer will say, I am looking at a Seyfert 2 narrow line radio galaxy. But if an astronomer were looking at it from this angle, he will say, I am looking at a Seyfert type 1 galaxy, which has broad emission lines. Here I have narrow emission lines. Some other astronomer looking straight down the pole will say, I'm looking at a blazar. I'm looking straight into the jet. So there will be tremendous Doppler boosting effect. And so this unified picture, consisting of an accretion disk surrounded by molecular torus and gas clouds falling into the black hole, explains rather successfully various types of AGNs, active galactic nuclei. So different manifestations are due to different viewing geometry. Now let us turn to the evidence for supermassive black holes. Although it became clear within a year after the discovery of quasars in 1963 that their central engines must be supermassive black holes, and there was evidence from variability, this evidence was not quite ironclad evidence. It was circumstantial evidence that if you pack that much mass into that smaller radius, it had to be a black hole or it will soon become a black hole. Over the years, observations made us probe closer and closer to the central black hole. And this argument could be made, the circumstantial evidence could be made a little tighter and a little tighter. Some years ago, a remarkable set of observations were made in galaxy NGC 4258. That's the galaxy that you see in this picture. Now, very close to the center of the galaxy, here is the galaxy, and we are looking right near the center of the galaxy, and that is expanded over there. What you see orbiting the central object, let's just call it a central object and not call it a black hole, are masers, water vapor masers. Yes, you heard me right. In interstellar space, there are masers. There are not only molecular clouds and molecular gas, but under the right circumstance, in the right environment, they function as masers. Therefore, masers have been functioning in nature for far longer than when Charlie Towns first made the maser. And so what you are seeing, these dots that you see, are water vapor masers. Now, the thing about water vapor masers is that because it's a maser, its emission line will be incredibly sharp. And therefore, you can measure Doppler velocities very, very accurately. So these masers, which I have marked in red, are moving away from us. So the accretion disk, or whatever it is, not accretion disk, the gas cloud, the molecular clouds, which are orbiting the central object, are orbiting in such a direction that these masers are accelerated away from us, and therefore their line emission is redshifted. Whereas these masers are coming towards us, and therefore the maser emission is blue shifted. So using these masers, and remember, look at this, these masers are available at various distances from the central massive body, you can determine the circular velocity. And what is plotted here is the radial, what is plotted here is the circular velocity or the tangential velocity as a function of distance from the central body. What you see is at large distances, the law of rotation precisely follows Kepler's laws. In other words, it's proportional to 1 over r squared. Remember when we discussed rotation curve of our galaxy and other galaxies, we talked about this, and we said the rotation curve does not fall as predicted by Kepler's laws, but remains flat, and that led us to the conclusion that there must be giant halo of dark matter around galaxy. So all we can say here is these masers, water vapor masers, are in perfect Keplerian orbits. They are sufficiently far away from the central body that there are no special relativistic effects, let alone general relativistic effects. So you cannot say for sure that you are orbiting a supermassive black hole. But what you can do, because you have beautiful Keplerian velocity curve, is you can deduce the mass of the central body very, very accurately. And let me remind you once again that these are very long baseline interferometers, because although your distance is still very large compared to the Schwarzschild radius, or a few times Schwarzschild radius, where general relativistic effects will begin to manifest, you are still sufficiently close enough. And to have that kind of an angular resolution, you need intercontinental baseline interferometry. Now, these are mega masers orbiting the central body in NGC 4258. These water vapor masers maze at a frequency of 22 gigahertz. Now, let me tell you a little story about this. Masers were first made by Professor Charlie Towns. Then many years later, he moved from MIT in Boston to University of California in Berkeley, where his interest shifted to astronomy. And there, one of his students was studying water vapor molecules in Orion Nebula. That night, there was a party that Professor Towns was having in his house for all his students because one of his students had just finished the PhD. But like Jocelyn Bell missed this party in her professor's house, this student missed the party in Professor Charlie Towns' house. So, in the midst of the party, when people are having a great time, the telephone rings and Professor Towns picks up the phone and his student says over the phone, "Prof, it's raining in Orion Nebula." That was his way of saying that there is so much water vapor in Orion Nebula and it's radiating like mad. And that was the discovery of the first water vapor maser in interstellar space. Now, because the maser lines are very short, velocities have been measured to an accuracy of 1 kilometers per second. And that's tremendous in an extragalactic context. From these observations, they were able to deduce that the inner edge of the observed disk has a circular velocity of 1080 kilometers per second. It's not relativistic speed, but it's moving awfully fast. The motion of the masers is perfectly Keplerian, and the mass of the central object is 3.6 times 10 to the power 7 solar mass. So it's a very massive body. Now the central object is almost certainly a black hole, but the evidence still remained circumstantial. Now we turn to the giant black hole at the center of M87. There is the giant elliptical galaxy M87. This galaxy is at the center of the Virgo cluster of galaxies. At the center of the cluster of galaxies, there is a giant elliptical galaxy, M87. Long time ago, astronomer Curtis noticed a linear feature, a line, pointing to the center of the galaxy, over there. That was in the early part of the 20th century. Long time ago. Today, you can look at that line using interferometry, and with the advent of interferometry, this linear feature that Curtis identified 100 years ago can now be identified with a jet. And later, X-ray astronomers looked at this jet, and one was able to say with certain degree of certainty that the jet is relativistic and it consists of plasma blobs which are being ejected by the central body that you see over there. This jet is one-sided, as we discussed in the previous lecture. You don't see this jet, but you see the manifestation of the jet because you see the radial lobe very clearly. But as far as the jet is concerned, you see only one jet. Now, this one-sided jet is seen over the entire electromagnetic spectrum. This is the X-ray jet with the Chandra Observatory, and you see the jet consists of blobs which are being ejected by the central object. This is a radio jet, and this is the jet seen in the visible wavelength by the Hubble Space Telescope. So this jet is seen over the entire electromagnetic spectrum, and it's a one-sided jet. Now, over the years, people have tried to look as close as possible to the central object and to look for finer and finer structures in the jet. So here is the radio galaxy M87. The giant elliptical galaxy is right there where the cursor is pointing. So you're talking about a very enormous size radio emission. And the size is 10 kiloparsec. That's about 10 kiloparsec. So this extent is about 70 or 80,000 parsecs. And that very central region has been mapped by using the Very Large Array in New Mexico in America. And that clearly shows a beautiful jet, just like in Cygnus A. And then astronomers have looked right near the central region of the jet using long baseline global interferometry. And in order to have high angular resolution, as I said in the previous lecture, you not only need long baselines, which you achieve by having telescopes in various continents on the Earth, but by also going to very high frequency, because the angular resolution is lambda by d, where d is the baseline and lambda is the wavelength of observation. So by going to higher and higher frequency or shorter and shorter wavelength, you can achieve higher and higher angular resolution. By going to 43 gigahertz, which is very high frequency observation for intercontinental baseline, they were able to achieve a resolution of, are you ready? 0.0003 seconds of arc. 0.003 seconds of arc. So incredibly high angular resolution, and that scale is 0.01 parsec. So you see, there is the central object. The central object is still not resolved. You still don't have enough resolution, but the jet near the central object is beautifully resolved. Now, if you want to resolve the central object, and if it is a black hole, if you want to have a resolution comparable to the size of the event horizon, which is the size of the black hole, then what is it that we are talking about? Very long baseline intercontinental interferometry at 43 gigahertz achieved a resolution of 3 times 10 to the power minus 4 arc second. That's what I said, 0.0003 seconds of arc. Now, various estimates had already suggested that the mass of the central body, if it were a black hole or whatever it may be, deduced from Eddington luminosity argument, must be of the order of or greater than 6 times 10 to the power 9 solar mass. Therefore, you can calculate what would be the Schwarzschild radius corresponding to that mass, 2gm divided by c squared. And then you can ask what will be the angular size subtended by the event horizon at the distance of the giant elliptical galaxy M87. Now, the angular size of such a black hole at the distance of M87 will be of the order of 4 to 7 times 10 to the power minus 6 arc seconds. So in terms of resolution, you're only at the resolution of 10 to the power minus 4 arc second. You really need to go to micro arc second resolution. So you need to do even better. Now, you cannot have a telescope larger than intercontinental baseline interferometer. That means you have to go to much higher frequency to achieve this increased resolution from 10 to the power minus 4 arc second to 10 to the power minus 6 arc seconds. Now, this poses formidable technical challenges. Now, I'm going to spend a couple of minutes explaining these challenges because it's all very nice to see beautiful pictures of images of black holes in the newspaper, television, and whatnot. But one forgets that all these things are possible because of tremendous advances in technology, in particular detector technology. So, what was finally achieved was very long baseline interferometry at a wavelength of 1.3 millimeters. 1.3 millimeters. And that was achieved by 2012 and 2015. VLBI was extended down to a wavelength of 1.3 millimeter. Now that has required many long-term technical developments. What are the kinds of challenges a radio astronomer faces when he tries to do intercontinental baseline interferometry at that kind of wavelength? Several. First of all, he has to deal with the noise in the receiver. You are looking at a celestial source and the signals are rather weak. Therefore, you cannot have a very noisy receiver because then the signal to noise ratio will be rather small. So you have to reduce the noise temperature of your receiver. And that's a whole game in itself. And that becomes harder and harder as you go to higher and higher frequencies because the intrinsic noise is greater. Secondly, as you go to higher and higher frequency or shorter and shorter wavelength like 1.3 millimeter, atmospheric opacity becomes greater and greater. Why? Because there are molecules in our atmosphere. There are water vapor molecules, there are carbon monoxide molecules, there are carbon dioxide molecules. They all have rotational levels. And these millimeter wave radiation from M87 will be absorbed by the molecules in our atmosphere. And this problem wasn't that severe when we are talking about longer wavelength. The atmospheric opacity was much smaller. Thirdly, the atmosphere is boiling. This is why the stars twinkle. And this twinkling of stars persists not just in visible wavelength, all the way up to radio wavelength, because the atmosphere has a certain refractive index, and these refractive index fluctuations in the atmosphere leads to fluctuations in the phase of a plane wave coming from M87 through our atmosphere to the radio telescope. And these fluctuations happen very, very rapidly, and the time scale is the time scale for turbulent cells to develop in our atmosphere. And the next complication is, if you want to have a reflecting telescope at 1.3 millimeter, the surface accuracy has to be very, very high. In the case of the giant meter wave radio telescope near Pune that I mentioned in the previous lecture, you are talking of low enough frequency that all you needed was a wire chicken mesh. That's enough to reflect the radio waves. But if you're talking of a millimeter wave telescope, then the surface accuracy has to be extremely high. And therefore, you can only build fairly small telescope. GMRT dish was 45 meters in diameter. The VLA dishes were 25 meters in diameter. But they were operating at a wavelength of centimeter. If you want to operate at the wavelength of a millimeter, then your dishes will likely to be 10 meters or 12 meters in size. Therefore, lambda by d, the angular resolution, will also be poorer because your d is small. So there are all these complications that you have to overcome. And that took a very long time, almost 20, 30 years. And finally, radio engineers licked all these problems. An angular resolution of 20 micro arc second was achieved at 1.3 millimeter. So from 10 to the power minus 4 arc second, they were able to come down to 2 times 10 to the power minus 5 arc second, which was a tremendous achievement. Now this was enough to resolve the shadow of the 10 to the power 9 solar mass black hole at the center of M87. Now, they observed this in 2015, and a ring of emission of diameter of 40 microarcsecond was observed. So they observed a ring of radiation, presumably an image of the black hole, whatever was radiating around the black hole. But your angular resolution was only 20 microarcsecond, and therefore you couldn't very well resolve the features in this ring. But that ring clearly showed a depression in the center. It seemed like a hollow ring, like a donut. And that was a signature of a shadow. And that depression was not seen very clearly. And that was because of poor baseline coverage. In other words, you didn't have telescopes of all the needed baselines to synthesize. So, radio astronomers came up with this new array, which is called the Event Horizon Telescope. The sole purpose of this telescope is to resolve the event horizon of supermassive black holes. And these are the telescopes that are part of this Event Horizon Telescope. They are located in various parts of the globe, and the locations are chosen so that they give you the right Fourier components. Among the many spectacular improvements the Event Horizon Telescope made compared to the usual very long baseline interferometry at 1.3 millimeter were the following. They had developed low noise detectors, and these detectors use superconducting insulator superconducting junctions. You might have heard of what is known as Josephson effect and Josephson junctions, made of sandwiching two superconductors between a normal insulator. And these are quantum detectors with very high signal-to-noise characteristics. The noise temperature of the receiver was decreased by going to quantum detectors by an order of magnitude at least. And the bandwidth of observation was increased by a factor of 30. Bandwidth, remember, is very important. So the signal-to-noise ratio is given by a well-known formula, 1 over square root of b tau, where b is the bandwidth and tau is the length of the observation. Now the signal is mixed in the superconducting junction, the Josephson junction, with a highly stable oscillator, just like in your radio, good old radio, super heterodyne receivers. The incoming signal is mixed with this oscillator signal generated inside your radio, and the beat frequencies are brought to much lower or intermediate frequency where it can be handled with more conventional amplifiers. The same was done over here, and there were various improvements central to the observation with the Event Horizon Telescope by 2017. In April 2017, this telescope was ready to observe the central region of M87. We have concluded from circumstantial evidence that right at the center of M87, there lurks a supermassive black hole. Let us recall what is the likely environment of the black hole, because the black hole itself doesn't emit any radiation. It is the radiation that emanates from the immediate vicinity of the black hole that we are concerned with. Therefore, let us look at the immediate vicinity of the black hole and its geometry. Now, the accreting matter captured by gravity of the black hole will form an accretion disk. I've said this many, many times. the angular momentum of the accretion disk, which will be perpendicular to the plane of the disk, may or may not coincide with the spin axis of the black hole. For example, in the case of neutron star, the accretion disk could be in a plane, that is, the normal to the accretion disk could be inclined with respect to the rotation axis. Now, matter flows inward in the disk due to some sort of a friction or viscosity, and the origin of this viscosity is still being debated. So please remember, gas of atoms and molecules orbiting in a disk in Keplerian orbit around the central body, they'll be in stable orbit. They will not come in and fall into the black hole. So you have to make this gas come closer and closer and closer. And for that you need some friction. Now, as the matter comes inward in this accretion disk, it will go faster and faster and faster. Therefore, its angular momentum will increase. Now, where did this angular momentum come from? Angular momentum cannot increase on its own. But because the matter is coming inward in the accretion disk, closer to the black hole, the increase in the angular momentum must be compensated by angular momentum which is flowing out of the system. So, even as some matter falls inwards towards the black hole, some matter will have to go out away from the black hole in order to conserve angular momentum. Now, if you go back to one of the 3 lectures I gave on galaxies, the third one on the spiral structure of galaxies, I said that one of the arguments that is being made is that the spiral structure is a consequence of stars moving away from the galaxy in response to the stars moving in towards the center of the galaxy in order to conserve angular momentum. Same thing happens here. Now, the temperature of the disk will be several million degrees. Now, it will mainly radiate X-rays. The mechanism will be collision between electrons and ions in the disk, or in other words, it will be Bremsstrahlung radiation, which we discussed in an earlier lecture. Now, the Chandra X-ray Observatory has detected many hundreds of such black holes with accretion disks, many hundreds of them. These include both stellar mass black holes as well as X-rays from the nuclei of galaxies, presumably harboring supermassive black holes. Very close to the black hole, I said that accretion disk will be very thick, puffed up due to radiation pressure. So that's the picture once again. There is a very large accretion disk. It is very thin, very close to the central body. The accretion disk is puffed up due to radiation pressure because it's hotter and hotter and hotter as you come closer and closer to the black hole, because the gas, as it spirals in, releases the gravitational binding energy, and therefore the gas gets hotter and hotter and hotter. So the gas here is much hotter than the gas there. Therefore, radiation pressure here is much more. Thus, the thick disk forms a nice funnel. Remember, this disk is puffed up to a dimension which is enormous compared to the size of the black hole. So that helps in presumably collimating the disk. The jet, excuse me. The conventional wisdom is that in the innermost region of the thick disk, the plasma is collisionless. In this region, the plasma is collisionless, and therefore there is no Bremsstrahlung. In order for Bremsstrahlung radiation to occur, there must be Coulomb collisions between electrons and ions. And theoretical physicists tell us, based on their modeling, that the innermost region of the accretion disk will be rather quiet as far as radiation is concerned. Now, the authors of the paper on the M87 black hole, whose picture you have all seen and which I shall show again, assume that the observed millimeter wave radiation, remember this whole observation is being made at a wavelength of 1.3 millimeter. What is this radiation due to? They assume that this millimeter wave radiation is synchrotron radiation produced by electrons gyrating in the magnetic field frozen into the accretion disk material. So, frozen into the accretion disk, there is a current loop, and this current loop gives rise to a magnetic field, and the electrons gyrate in this magnetic field, producing synchrotron radiation. So, that's the origin of the 1.3 millimeter wave radiation that we observe. Now, the observed spectrum of radiation, intensity as a function of frequency, is a power law, signature of synchrotron radiation. The radiation is also highly polarized, again a signature of synchrotron radiation. And both these things, the spectrum and polarization, support the hypothesis that the observed millimeter wave radiation is indeed synchrotron radiation. Thus, there is a thick torus surrounding the black hole. The plasma in the torus will also be rotating around the central black hole. The sense of rotation may or may not coincide with the sense of rotation of the black hole. So the curved black hole has a certain angular momentum and a spin axis. The sense of the angular momentum of the torus may or may not coincide with the spin axis of the black hole. Excuse me, please. Near the event horizon, the rotational velocity of the gas will be relativistic, and therefore we will expect Doppler boosting effects. Now, what does one expect to see with the Event Horizon Telescope? Let us first recall some of the things that we learned about black hole. Now, let us recall the motion of light near a Schwarzschild black hole, a non-rotating black hole. There is the black hole of a certain mass. Schwarzschild radius is 2 gm by c square. Now, photons are coming in from the left at various impact parameters. Impact parameter is the distance between the line and the black hole. This distance corresponds to the impact parameter if there is no deflection of light. Now, I said that there is a critical impact parameter. The impact parameter could be over there, and this is a critical impact parameter. The value of the critical impact parameter is a precise number. For a Schwarzschild black hole is 3 square root of 3 divided by 2 times the Schwarzschild radius, which is 2 gm by c square. And that result comes from general relativity. Now, if you look at a photon which is coming from infinity at the critical impact parameter, it will go around the Schwarzschild black hole, and then once in a while it might actually escape. So that is the concept of the last stable circular orbit, whose radius is 3 by 2 times the Schwarzschild radius. This is what I had told you before. So please keep this in mind. Now let's look at this again. Now I am going to say that this will result in a shadow of the black hole. The shadow itself will be much larger in diameter than the diameter of the black hole itself. So the reason why the shadow occurs is because of this concept of the critical impact parameter. So now let's look at this once again. So there is the black hole's event horizon size multiplied by 1.5. So this is 1.5 times the Schwarzschild radius. And there is the photon cloud. In other words, whatever collapsed to become the giant black hole, the light it emitted is still light it emitted when its radius was 1.5 times the Schwarzschild radius. Those photons are still circling the black hole. They are severely reddened, and once in a while that photon may escape. Now let's look at what we expect to see. So let's keep this figure over there to remind ourselves of the various orbits of photons. We're still talking about a Schwarzschild black hole. So there is the black hole, and that is its size. That is the event horizon. 1.5 times larger than the event horizon radius is the photon cloud. So this is the last stable circular orbit of photons around the black hole. And then there is the shadow. And the size of the shadow, the radius of the shadow, will be the critical impact parameter 3 square root of 3 by 2 times the Schwarzschild radius. So the shadow corresponds to this size. So the black hole shadow is a lot bigger than the physical size of the black hole itself because of the orbits that are shown over there. So ideally, that's what you should see. And surrounding the shadow, you will see radiation which is coming from this gas which is going around the black hole, this torus. But now we must keep in mind that this black hole is not likely to be a Schwarzschild black hole, but it's likely to be a Kerr black hole with maximum possible angular momentum. So if you recall, for a Kerr black hole, there are two surfaces. There is a static limit, and then inside that is the event horizon. And the region in between is the event horizon. This is the view seen in the equatorial plane. If you look at the same thing from, say, the North Pole, then that's what you would see. This is the event horizon, whose radius is half times the Schwarzschild radius, and then this is the static limit, whose radius is equal to the Schwarzschild radius. So that is the black hole itself. Now let's remember what I told you about the orbit of light around a rotating black hole. Imagine a stone or photon coming in radially from infinity. When it comes close enough to the black hole, it will acquire angular momentum because although initially it had no angular momentum, space inertial frames themselves are being dragged by the rotating body, and therefore this will be the trajectory of the photon. All right? So this is the example of angular motion without angular momentum. Now, what does one expect to see? Long before these observations, which were done in 2017, Falke and his collaborators in the year 2000 studied this problem. And they said, this is what you should expect to see if someday you had a telescope with an angular resolution to see very close to the black hole. For an accreting black hole embedded in a geometrically thick, optically thin emission region, There is a thick accretion disk, but optically thin. Optical depth tau is very small compared to 1. The combination of an event horizon at the center and light bending leads to the appearance of a dark shadow, as we have just seen, together with a bright emission ring. So they said there will be an emission ring. At the center of it, there will be no emission. That's because there is a shadow. It should be detectable by very long baseline interferometry experiment. Its shape may appear as a crescent, not as a uniformly bright ring. It might appear as a crescent, meaning in some places you don't see the ring at all. In other places you see the ring and it's very bright. And this crescent-shaped ring may be because of very rapid rotation and relativistic beaming, which results in Doppler boosting of intensities. So this is what they said in their paper. So you would expect to see something like this. You would see a bright ring, brighter in some region than in the other region. The central region corresponds to the shadow of the event horizon. The shadow of the event horizon, of course, is much bigger. Is 3 root 3 by 2 times the Schwarzschild radius. That is the radius of this shadow. So this is what they said in their paper in the year 2000. In 2017, what did radio astronomers observe? The paper actually appeared 2 years later in 2019. It's not because there was anything funny going on. It took that long to analyze the data. And many different astronomers had to observe it and agree on the conclusions before the paper was submitted for publication, which is the signature of solid science. And this is the image that was published in 2019. A crescent-shaped ring with presumably what is the shadow of the black hole at the center. Now, what would you have expected based on the Falke et al. Paper for this particular black hole? Various computer simulations were done of a geometrically thick torus of gas, which is optically thin, emitting synchrotron radiation at 1.3 millimeter wavelength. And this simulated image is based upon general relativistic magnetohydrodynamic calculation. So this gas in the thick torus is highly turbulent and it's highly relativistic. So the hydrodynamic has to be done in the framework of general relativity. So it is a very hard calculation. General relativistic magnetohydrodynamics. Magnetohydrodynamics is complicated enough subject, but to do that within general relativity is far more complicated. So this is what the theorists had calculated for M87 black hole. But the theorists had assumed an angular resolution was infinite angular resolution. But they knew that the observations that were done using the Event Horizon Telescope had an angular resolution of 20 micro-arc second. Therefore, in order to compare this theoretical prediction with this observation, you have to make this fuzzier to an equivalent resolution of 20 micro-arc second. All right, so you deliberately make it fuzzier. You make the angular resolution poorer so that the resultant angular resolution is equal to the angular resolution of the observation. And when done, that's what the theory predicts. So the simulated image using general relativistic magnetohydrodynamics convolved with 20 micro-arc second resolution gives this. You must agree that the simulation is in beautiful agreement with observations. So, what has gone into this simulation? What can we say about the accretion disk? Its sense of rotation and the angle of observation in relation to the accretion disk. In other words, when I do a simulation, I have to assume many things about the geometry. So, for example, here is a black hole. The black hole itself could be spinning in that direction about that axis. Here is the gas in the torus. That could also be spinning about the same axis in the same direction. That would give me a crescent-shaped ring like this. On the other hand, if the black hole spin axis is this, pointing to the right, and if the black hole is spinning like this, and if the matter in the torus is spinning now in an opposite direction, then I will get a crescent-shaped ring which is over there. Similarly, I could have this geometry. Similarly, I could have this geometry. So, I have to do the simulation for all possible geometries of the axis of rotation of the black hole, the axis of rotation of the torus, and their relative alignments. So here is the final result. The simulation convolved to 20 micro-arcsecond resolution, which agrees excellently well with observations. This particular simulation corresponds to the following. There is a supermassive black hole at the center, and its spin axis is pointing in that direction. And there is the torus, the innermost part of the accretion disk, which is puffed up due to radiation pressure. That is the gas torus. Comparison with simulation suggests that the torus is rotating clockwise around the spin axis of the black hole. So the torus is rotating in the same sense as the black hole itself, and the axis of rotation of the torus is pointing along the spin axis of the black hole. This is what the simulation, which agrees with observation, suggests. And that is the line of sight from us to M87. And that line of sight makes an angle of 17 degrees with the spin axis of the black hole. So it is this geometry in which the simulations agree with observations. So what is the summary of conclusions? The shadow is caused by a curved black hole, by a rotating black hole, with the spin pointing in the direction of the receding jet. Remember, we see a one-sided jet in M87. The jet that we see is presumably coming towards us. So the jet is ejected along that axis. There is a component of that velocity in this direction, the radial velocity v cos theta, that causes tremendous Doppler boosting of intensities, and we see the jet. There is also a jet going in that other direction, which we do not see, because if you now resolve that into that direction, then it will not be Doppler boosted. Therefore, we can say that the shadow is caused by a rotating black hole with the spin axis pointing in the direction of the jet that we do not see. They are bound on the spin of the black hole. The paper says they are bound on the angular momentum of the black hole. They conclude that our line of sight is most likely inclined to the axis of the jet by 17 degrees. The observed millimeter wave radiation is synchrotron radiation and emanates from within a few Schwarzschild radii of the black hole. The emitting plasma is collisionless and optically thin. Plasma is rotating in the clockwise direction, resulting in the brightening of the lower portion of the ring because of Doppler boosting. They derive a good estimate for the mass of the central black hole, and that mass is 6.5 times 10 to the power 9 times the solar mass. Now that is M87. Now let us look at the black hole at the center of our Milky Way galaxy. There was strong circumstantial evidence now for more than 30 years that there is a 3 million solar mass black hole at the center of our galaxy. The evidence was circumstantial. Now, in recent years, using very clever and ingenious adaptive optic technique in the near infrared, astronomers have been able to study the motion of stars very close to this central black hole. Most of the stars which we see in the sky are in our backyard, just a few light years away. This is because of strong extinction by dust. So if you want to see as far as the center of the galaxy, which is at a distance of almost 30,000 light years, then you have to see in the infrared. And you have to have incredibly high angular resolution. You must have adaptive optics, which gets rid of the turbulence in our atmosphere. To be fair, till recently, we did not have any conclusive evidence for the existence of supermassive black holes. These are very remarkable observations of stars orbiting the central black hole. There is the central black hole, that star there, and these are different stars, 1, 2, 3, 4, 5, 6, 7 shown here, orbiting in different directions. These various dots correspond to the position of the stars at various times. From that you can deduce the velocity and indeed the acceleration. Genzel and Andreas Ghez and their collaborators observed the motion of stars in orbit around the dynamical center of a galaxy using infrared techniques that had been developed by Professor Towns and his group using adaptive optics. These were exceedingly difficult observations requiring very innovative instrumentation. And they had to observe and gather data for more than a decade. So here is the center of the galaxy. And here is an expanded view. What you see here are stars orbiting right there near the center, and they have been able to deduce both their velocities and accelerations. What did they find? That there is a very compact object at the dynamical center of our galaxy. It is very massive. Its mass is 4.100 plus or minus 0.034 million solar masses. Such a black hole with such a large mass, the compact object had to be a black hole. And for this, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize for Physics in 2020, which they shared with Roger Penrose. And the citation for their Nobel Prize read as follows: for the discovery of a supermassive compact object at the center of our galaxy. Very recently, on the 12th of May of this year, 2022, you have all seen this image in newspapers and television of the image of the shadow of the central black hole at the center of our galaxy, once again using the Whole Earth Telescope. And I'm sure soon we will get such images from many other galaxies. Now, in conclusion, let me say a few words about the formation of such supermassive black hole, because that is really the key question. Supermassive black holes are formed through series of mergers of black holes that resides in the centers of galaxies when galaxies collide. If you look at a deep image taken with the Hubble Space Telescope, you see galaxies in the early universe. And most of those galaxies you see are in collision with other galaxies. So the collision and mergers of galaxies was a very common event long time ago. And each galaxy presumably had a central black hole, and these two black holes then coalesced due to dynamical friction that I talked about, the two black holes spiraling in and merging, emitting a burst of gravitational radiation, which we shall discuss soon. And so the mass of the black hole is now the sum of the masses of the two black holes. And if this goes on for a long time, the mass of the black hole will grow. But then you have to ask this naughty question. How did the original black holes form? Now, one possibility is that stars formed first, and then stellar evolution led to black holes, and those black holes merged with other black holes, formed the first supermassive black hole in the center of a particular galaxy. But there is a problem with that. While such a scenario is more than plausible and suggested long time ago, there is an embarrassing difficulty. Now, with the Hubble Space Telescope, we have been able to see galaxies farther and farther away. That means formed at earlier and earlier times, at larger and larger redshifts. We have also been able to see quasars with redshift of 6 or more. The first quasar to be discovered had a redshift of 0.1, and that created a sensation. It was a revolutionary discovery. Now we are talking about a quasar with a redshift of 6. Now, when you talk of a galaxy or a quasar at a redshift of 6, it means you're talking about a universe which is less than 1 billion years old. Less than 1 billion years old. The present age of the universe is 14 billion years. You're talking about galaxies and quasars forming in less than 1 billion years. When you're talking of a quasar blazing away at less than 1 billion years, you're saying a supermassive black hole has already formed in less than 1 billion years. Now, that is a serious difficulty, because in order for a black hole to form, matter must fall in, and you can estimate what will be the free fall timescale using Newton's laws or general relativity. The difficulty is the free fall time to form the black hole is much greater than the age of the universe at that time, which was only a fraction of 1 billion years. So, galaxies as we see them today would not have formed that early on. Yes, there were some collapsed objects, but they were not galaxies in the sense that we see today. And yet, black holes formed at their centers because they were quasars radiating at a redshift of 6. Clearly, this rules out mergers that far back in time. You can't say that the supermassive black hole, when the age of the universe was only 0.75 billion years, was formed due to many generations of mergers and mergers. So that black hole must have formed in some other mechanism. So one possibility is that original supermassive black hole in primitive galaxies might have formed from the collapse of a supermassive star, a star whose mass was not a few times solar mass, but 10 to the 9 times the solar mass. Now, such a supermassive star, will be supported entirely by radiation pressure. Radiation pressure is due to photons. The gamma, the ratio of specific heat of photons, is 4/3. Now, if you remember my earlier discussion of stability of matter which has a gamma of 4/3, like for a white dwarf with a Chandrasekhar limiting mass, is highly unstable to gravitational collapse. Now, as this supermassive star collapses, at some stage it will become unstable and collapse. What is the criterion for stability? So let me recall what I said before. In Newtonian theory, for a star to be stable, the average value of gamma, the ratio of specific heat, should be greater than 4 by 3. If gamma is less than 4 by 3, the compressibility of matter becomes negative, and then the matter will become unstable to dynamical collapse. So here is gamma on the y-axis, the ratio of specific heat, plotted as a function of the logarithm of the density on the x-axis. The horizontal dashed line is the critical value of gamma in Newtonian gravitational theory. So all that is stable, all this is unstable because gamma is less than 4 by 3. But now we are talking of a star so massive that you have to discuss stability not in Newtonian theory, but in general relativity. Now, this problem was first discussed by Chandrasekhar in the 1960s, rather rigorously. And what he found was that in general relativity, the critical value of gamma is not 4 by 3, but 4 by 3 plus a factor, which is some number, kappa, multiplied with the Schwarzschild radius divided by the radius of the star. So, as the radius of the star approaches the Schwarzschild radius, this correction to gamma becomes very important. So, let me say this through a figure. This dashed line is the stability limit in Newtonian gravity. So, when gamma becomes equal to 4 by 3, matter will become unstable. Stability limit in general relativity is 4 by 3 plus some correction, which is that dashed yellow line. Therefore, matter becomes unstable right over there at that value of gamma. So, this is now unstable. So, the point I'm making that in general relativity, the star is more prone to a dynamical collapse because gravity is stronger, and that raises the stability limit for gamma from 4/3 to some 4/3 plus kappa. Therefore, a supermassive star, which is supported by radiation pressure for which gamma is already 4 by 3, will eventually collapse due to general relativistic instability. And this was pointed out by Chandrasekhar a long time ago. Whereas there are many difficulties with this scenario, 50 years after quasars were discovered, no one has a better idea to form the very early black hole other than to suggest that they formed from a supermassive star. So to end this lecture, I apologize for going on much longer than usual, but I didn't want to split this into 2 lectures. Let me end this by quoting Chandrasekhar about black holes, and I shall read it for you. Black holes are macroscopic objects with masses varying from a few solar masses to millions of solar masses. To the extent they may be considered as stationary and isolated, to that extent they are, every single one of them, described by the Kerr solution. This is the only instance we have of an exact description of a macroscopic object. Macroscopic objects, as we see all around us, are governed by a variety of forces derived from a variety of approximations to a variety of physical theories. In contrast, the only elements in the construction of black holes are our basic concepts of space and time. They are, thus, almost by definition, the most perfect macroscopic objects. They are there are in the universe. And since the general theory of relativity provides a single, unique, two-parameter family of solutions for the description, the Kerr metric, they are the simplest objects as well. So these are the black holes, beautiful and perfect objects. So with that, we conclude our discussion of radio galaxies and what is at their centers, the realm of the supermassive black hole. In the next lecture, we shall go to a completely different topic. I will tell you a remarkable detective story, a remarkable story of the case of the missing neutrinos from the sun. And this has led to a very great difficulty for the standard model of physics. So until then, thank you for your attention.